All right, so my name is Searle, and as you mentioned, I work for an organization, actually one of the managing partners of an organization called Utilisec. We specialize in doing security consulting and penetration testing for the energy sector, so electric utilities as well as vendors that are selling to the electric utilities. So really the purpose of this talk is to try to provide some more information for everybody to be able to get into this field. Out of curiosity, how many people in here are penetration testers? By raise your hands. Or that do security assessments of any sort. Okay. One of the things that we have is unfortunately many people are in the security field doing security assessments for other organizations and other markets. However, very few people are inside of the energy market in the SCADA and the smart grid realm. This is something that we need to address because we need more people testing these critical infrastructure, critical systems. Because these systems are the ones that can cause mass damage in the real world if they have been hacked. So we need more people inside of this field. We need more organizations to be able to gain these skills and to perform these penetration tests. So one of the primary goals of today, need more? Yeah, better. So one of the primary goals of this presentation is to provide everybody some knowledge to understand how they can take their current existing skills and apply them to the energy sector in SCADA and smart grid, as well as provide you more information on what types of additional skills you can gain where you can look for. So first off, I'm going to take you through an architecture of what the smart grid looks like. Most people have heard of SCADA and are familiar with SCADA. However, SCADA is a very small piece of the overall infrastructure inside of the energy sector and these systems that are being deployed. They're not the only critical piece that can be attacked by attackers. So when we look at critical systems inside of the energy sector, many of these can be broken into major key players inside of the field. So this diagram on the screen shows that there are several different players here. If you look on the top left, there's actually markets inside of the energy field. There's several different organizations that generate electricity, sell that electricity back to the utilities themselves, distribute them across our nations and our borders, down to the individual companies selling electricity to our homes and to our businesses. Okay? These markets are one area that can be attacked by attackers. Very similar to getting into the stock markets and crashing the stock markets could have huge consequences. The same thing can happen inside of the energy sector. We have operations which control the majority of the energy being transferred across. This is another organization, another part that can be attacked. Service providers, usually organizations that sell services directly to organizations and users. And then across the bottom, if you look on this diagram, you'll see the dotted yellow line. This is the power that flows from the bulk generation where it's being generated to the customer, whether that's a residential home or a business. So between that, there's usually several different stages. In the United States, we commonly divide them into two major categories, the transmission operators and the distribution operators. This division is fairly true across the world in most countries. I'm not sure how it is here in India. I haven't had a lot of exposure to the organizations here in India. However, in Europe, this is a very common way to divide them as well between transmission and distribution. And then, of course, there are several different smaller subdivisions inside of there. And then finally, there's the customer itself that's consuming the electricity, the residential users, the corporate users, the industrial users, the manufacturers. Okay, all of these provide different entities and different people that can be attacked. Any attack inside of this chain can affect the electricity being consumed by the consumer at the very end of the chain. So now this diagram shows a little bit better view of the different types of systems that are in play in the majority of these critical infrastructures. Okay, you can see that each one of the clouds represents the same object that we had in the previous diagram. They've been shuffled around a little bit to be able to make it so that we can portray everything. You can see in the very center, operations is kind of the key where the majority of the systems are. Okay, then we have all the different other players that we just previously spoke about around the edges. Now, what I'm going to do is show you where the different types of technologies are. Everybody has heard of SCADA. That's not a new term to individuals. Okay, when we look at SCADA, okay, these are all the systems and all the communications back and forth. And when we look at SCADA, this is where our SCADA systems are the areas highlighted in red. Okay, so the distribution SCADA, if you look right in the middle, that box labeled number 29, okay, that is the control servers for the SCADA systems. Many of the attacks that we've heard of, like Stuxnet and the other types of vulnerabilities, are targeting these systems. These systems are running commodity operating systems like Windows and Linux. The same skills, the same exploits that we have that we can attack Windows machines and Linux machines can be used to attack these systems as well. Okay? That's true for penetration testers like myself. That's true for malicious attackers out in the world. Okay? So these are the primary targets. When we get to the field devices, some of these other blue boxes and the green boxes, these are other types of systems that are out in the field that can be attacked. For those that have been watching the news, there were some vulnerabilities that were released for some PLCs just a few weeks ago at a conference in the US called S4, which is actually an energy sector specific conference. These vulnerabilities that were released were vulnerabilities that affect some of these end systems. Okay, so you can see the PLCs right up here, the RTUs, the IEDs, and the PLCs that are usually connected to those devices. That's where those vulnerabilities took place that they were discussing at the S4 conference a few weeks ago. Okay, other things, we hear a lot about electric vehicles. Electric vehicle is something that is gaining a lot of traction both in the United States and across Europe. They're not widely deployed yet, however they are starting to be deployed and are commonly available for those that can afford them. They're very, very expensive cars and they're not very economical to drive sometimes yet. However, the future for smart grids or these electric vehicles are that a lot of the electric utilities are hoping to leverage and use these electric vehicles to try to provide more benefit to the grid. For instance, one of the technologies that the electric utilities are looking at is if you have an electric vehicle, when you drive that electric vehicle back to your house and you plug it in, instead of immediately recharging the battery of the electric vehicle, usually everybody gets home around the afternoon, which is usually the peak time for electricity, the most expensive time for electricity. Instead of having these vehicles start immediately recharging, instead what the electric utilities are hoping to do, and they're working with manufacturers to make this happen, is to have the remaining battery resources inside of your vehicle be used by your home. So your home can use the remaining electricity inside of your vehicle. Okay, this is something that will be offered by choice, because if you have to go somewhere in just an hour, then of course that's not going to be very, very feasible. But that's the hope that for consumers, instead of having to buy electricity during the most expensive time, they can simply have their home use the electricity that's remaining inside of their electric vehicle. And then during the middle of the night when we are sleeping, which is usually the cheapest time to buy electricity, then it will recharge the electric vehicle so that you're ready to take the vehicle to work the next morning. That's one technology that they're looking at. And when we have functionality like that, once again, that's more functionality that can be attacked. So that's one thing that we're looking at inside of electric vehicles, is how that functionality can be attacked. They're also looking at payment models where in the United States, this is something that the United States is one of the only ones pursuing this right now that I'm aware of, but they're trying to get a model where that you can plug your electric vehicle into anybody's house. And when you plug it into somebody else's house, it doesn't charge them for that electricity, it charges yourself. In order to do that, there has to be communication between the vehicle and the home and the electric utility, which are communication channels that can be attacked. So this is something else that we do a lot of penetration testing for. Synchrophasers is a newer technology. For those that are into electronics, the easiest way to describe what a synchrophaser is if you're familiar with what a digital multimeter does, it gives you a reading of what the electricity is inside of a circuit, and it will give that in a digital format. That's basically how they're currently measuring and monitoring the grid right now. That's what the SCADA systems are monitoring, is more or less readings like a digital multimeter every 2 to 3 minutes. What they want to do is they want to have more fine-grained view of what that power consumption, power usage really is. So they're looking at technologies like synchrophasers that basically provide more of an oscilloscope view. Okay, they're taking measurements every 30 times per second up to 240 times per second. So that way they can actually see the waveforms to see exactly what's going on inside of the electricity and the consumption of the grid. Back in the United States, we had a very huge power outage about 8 to 10 years ago on the eastern coast that was down for a couple days. And this outage they believe could have been prevented if they had the synchrophasers. These synchrophaser systems, if they had the more fine-grained measurements, they would be able to see a few hours in advance before the whole tower went down across the grid on the eastern border of the United States. So these are new technologies. Once again, another technology that can be attacked. These are using GPS signals to be able to get their time measurements so that when they're measuring the waveforms, they can actually get the exact same time on that waveform as they do all the other substations they have with these synchrophasers. So by attacking the GPS signals, and the timing of the GPS signals can be attacked, as well as the communications. And then finally, the smart meters themselves, a newer technology trying to give electric utilities more visibility into how electricity is being used in their homes. There's privacy concerns here, there's security concerns here, but there's a lot of benefits for the consumers themselves. This is something that I like to see. Personally at my house, I like to try to monitor everything inside of my house so I know when I have my energy bill, what devices inside of my house are consuming all the energy. I have a full-size rack server inside of my house, and I always want to know how much power is that server being used when I add a new server to it. Same thing with buying a new appliance. How much electricity is really being used here? So this is something that smart meters can be used for. Okay, so if we want to look a little more detail inside of the smart meters, here's a diagram of what the smart meter technologies look like in their systems and how they're architected. If you look on the far right-hand side, you'll see that those are the meters themselves that are being deployed. There's several different communication methods for these meters to communicate back to the electric utility. Some of them are using a mesh network. Some of them are using communications over power lines. Some of them are for larger industrial locations are literally using leased lines to communicate back to the electric utility. And then some we're starting to see are being deployed with cellular modems directly in every single meter that's being deployed. So every single meter can basically send a cell phone data packet back to the electric utility with that consumption information. In the United States, most of the electric utilities are looking at this technology to measure electricity in the home up to once per 15 minutes. So that's not very fine-grained. A few weeks ago, there was a security conference back in Europe that they were talking about how they can fingerprint which movies you're watching based on your smart meter. Okay, this is a type of smart meter that's not commonly being deployed. This smart meter that they were hacking, the reason why they're able to do that and be able to fingerprint what movies were being watched is because these smart meters that were being deployed weren't the ones like these ones that are commonly deployed across the US and across Europe. They were kind of more of a smaller solution that's trying to gain traction, that instead of using wireless communications back to the electric utility, they leverage your internet inside of your house. The meters specifically that they attacked were taking meter readings once every 2 seconds. Okay? And most of the ones for most smart grid are only once every 15 minutes. And at reading once every 15 minutes, there's no way you can fingerprint what movie you're watching. It's just not realistic. You might be able to fingerprint some of the appliances that are being used. But these meters, whichever technology you're using, they usually come back to an aggregation point, which is a takeout point. So there might be one aggregation point per neighborhood. And that aggregation point will collect all the information from all the meters and then send that back over some type of a backhaul, usually a cellular connection, back to the electric utility, which is running their servers that are controlling it. The servers that control the smart meters are commonly called head-ends. Sometimes it's one single server. More commonly, that head-end is actually a cluster of different servers, each server with its own separate function. Also in this diagram, you can see in the lower area, these are the common network protocols that we'll see. Most of the solutions only use a few of these, but this is kind of a summary of many of the solutions that we actually see and we perform testing on. And then finally, in an AMI network, a smart meter network, this is the type of data flows we commonly see. So the arrows across the bottom shows what type of data is flowing between which actors. So this is a generic diagram that shows the data flows that we usually find in almost every single smart grid system. Okay, the ones at the very bottom, the threes at the very bottom, these are additional services or additional functions that electric utilities are considering deploying, and in some cases are starting to deploy, that leverage the AMI network or the smart meter network to send the data back and forth. So for instance, they might send data from appliances inside of your house. They call them manned response appliances inside of your house. They may send that information back to the electric utility via the smart grid network. They're also sometimes using some of the substations The substations are where all the power comes to inside of your neighborhood. So if you usually see, I've seen them here as I've been traveling across India, substations here, usually areas where the big power lines come to, and they have a little fenced area with all sorts of different equipment. Those are called substations. Some of the electric utilities inside of the US and in Europe are starting to deploy technologies to take information collected at that substation and send it across the smart meter network as well, where traditionally they had a completely separate network, and generally that's our recommendation to the utilities, because we feel it's a little more safer having a separate network and not leveraging the smart meters. But economics, they have a network, they want to use it to save money. So that's kind of a summary of what the smart grid is and all the different technologies we have. Now what I want to do is share with you a testing methodology that we've created. These testing methodologies are the methodologies that Utilisec, our company, uses as we perform penetration testing inside of the smart grid appliances. This can apply to SCADA systems, this can apply to smart meter systems, sinker phasers to electric vehicles, pretty much any system inside of the area, inside of the smart grid. So if anybody wants more information on this, please feel free to contact me. This actually is attached to a much larger document that actually goes through and explains each one of these tasks that I'm going to talk about here briefly in the slides. This is freely distributed. This is freely available online. This is a document that I actually created for Department of Energy inside of the United States for guidance to all the electric utilities on how to perform penetration tests and how to plan for these penetration tests. So this is something, please freely use this here. Anybody that's doing work inside of this, or if we have anybody working in the energy sector, please leverage this information and put it to use here in India. And you'll get back to us if you see changes in the way that you do things here in India. Get back to us and we can make this an international document that's more applicable to everybody. So here, if we look at an overall penetration test, if we do a full penetration test of all the systems or all the components, what I would call a comprehensive penetration test, usually what I will do is we'll do a comprehensive on just one single system. So we'll do it on the smart meter system, or we'll do it on the SCADA system, or we'll do it on the electric vehicle systems. Okay? We'll take this, let's say for instance, let's talk about the smart meters. It might be a little easier since you've seen a diagram of the servers and the components that are being used. What we'll do is we'll take the penetration test of this entire system and break it into major phases. Okay, this describes the major phases I often break the penetration testing into when I'm doing scoping on an engagement. I break this into 4 different categories. You can see there's 4 smaller boxes across the middle based on the skill set of the penetration team, testing team that we have performing the work. Okay, so on the left-hand side, this is the embedded penetration testing. This is physically attacking the electronics of any of the field deployed devices. Primarily, this is going to be the smart meters, but this can be the aggregation points or the access points that are being deployed in the field as well. Anything that attackers can get their physical hands on can be attacked. And so this is something that we will often do for electric utilities. We have the orange box up there. Doesn't look very orange up there on the projector screen. So the network communications penetration tests. This is where we are looking at the communications, capturing the communication, the network communications, and analyzing that communications for vulnerabilities and flaws. Then we have the server penetration test, where we're looking at the operating systems and the traditional services that are running on that operating system. And then we look at the applications, the server applications. These are going to be the web servers, the web services, the user interfaces, the machine-to-machine interfaces between the servers. That's going to be the application penetration test. Each one represents totally different skill sets. Many penetration testers will have the capability of performing the operating system penetration test. This is a common penetration test most of us that are testers perform all the time. Many of us have skill sets to be able to test web applications. Okay, so that's the applications. The skill sets that aren't as common, the network communications. 5-10 years ago, it was much more common to test these. For some reason today, not many people are looking at the network protocols anymore. We still have it, there's still a lot of good research, but most penetration testing usually looks at the endpoints and don't look at the communication traffic itself. And then the embedded, this is something that's a much newer field. There's very few people performing penetration tests on embedded systems. This is something that's a lot of fun. There's a lot of good information here. There's a lot of need for people to write tools inside of this area. So there's a very, very good area to grow into if it's something you're interested in. Okay, now I'm going to go through each one of those sub-tasks and just kind of dig into each one to show you some of the things that we're performing during our tests in each one of these. Okay, so here's when we're looking at the server operating system. Okay, we'll go through and do some information gathering, some vulnerability analysis and exploitation. Okay, this is no different than what you were doing in the operating systems themselves. Okay, like I said, most of these control servers are running Windows and Linux. When we're testing the operating system, there's not much difference here. The biggest difference is you just have to be very careful not to knock the system over, because that could have consequences down the line. Or once you have gained access and gained a shell or gained root on one of these systems, you have to be very careful not to mess with some of the services that may cause consequences down the line. Many times when we're testing the systems, our new systems are going to be deployed, and we don't do a lot of testing on production systems, but if you are doing testing on production systems, which we do recommend doing, you want to make sure that you do that very carefully, be very careful of automated tools, and make sure that everybody is aware of that the tests are being performed, so that people can be on hand to bring power back up or restore any issues that are caused. So something that has to be done very, very carefully. You have to be very familiar with all of your tools before you use those tools. Don't use tools that you're not used to knowing, because you just don't want to knock these systems over very bad. Okay, so this is some of the server operating systems tests. Once again, none of this should be any different than what most of you are looking at. For those that are familiar with the pen test standard, the P-test, a newer project that's been going on for the last year that I've been participating in, this is in line with the P-test work. So it was a way that I could actually try to bring the work we were doing in the penetration testing standard and bring this back and try to codify it and bring it to the energy sector. So this is now has a permanent home inside of guidance documentation for the energy sector. So here we look at the applications, the server applications themselves. These are the web applications, the web services. Once again, there's not a lot of differences here. The biggest difference is when you're running fully automated tools. When you're running fully automated tools on the web applications, you have to be extremely careful that the automated tools aren't going to go through and touch the pages that are sensitive pages. For instance, when you're looking at a smart meter web application back on the controlling server, the way you shut down power for the house is by clicking on a link that makes a post request. If you have an automated tool attempt to make every single post request, which they do by default, it will try to go through and shut down power for every single meter's interface page it gets to. So this is something that you don't want to run automated tools on the web interfaces when you're doing this on production systems, or even when you're doing it on non-production systems and testing and staging environments. You generally want to do your web application assessments with primarily your manual techniques and your semi-automated tools that you have full control over what they're playing with. You don't generally want to go through and run a large commercial tool like your web inspect or your app scan, some of these large tools. You don't want to just simply blindly point them at the application, because they will actually start making problems or sending firmware updates out to the devices, which is very bad. Okay, when I do a web application assessment, whether this is energy sector or outside of energy sector, I still do a lot of web application assessments outside of energy sector. This is the methodology that I use. This is also in line of what OWASP teaches inside of their guidance document and what we teach inside of the SANS courses that we teach. So basically, we map the application and gain that understanding of the application. We then go through and start doing discovery of the application, looking for the different vulnerabilities. And then we will go through and start doing exploitation of any of the vulnerabilities that we find. So this diagram breaks it down into some of the smaller components and some of the smaller tasks that we perform. And just as an example, one thing that we are always looking for, cross-site request forgery is a problem that is a vulnerability in almost every single web application out there, even across the internet. This is probably one of the most commonly found vulnerabilities in applications. And it's something that not all penetration testers are testing for yet. So this is something we've known about for several years. Please, if you're doing a penetration test, look for cross-site request forgery. Do some Google searches to learn about it. These are things that we're finding all over the place. I will test an application that has been tested by 3 or 4 other firms doing penetration testing. And there's cross-site request forgery on all their sensitive pages, which none of the other firms have ever found. So please look for this. One example of the cross-site request forgery, something we're concerned with inside of the energy sector, is if you have a customer service agent which has capabilities to be able to shut down power remotely at a house on their web interface, if they're also surfing around online, an attacker could simply call up to one of these customer service agents and talk to them and convince them to surf to some web page. Tell them, hey, start talking about your family and share a picture of your family. Hey, you can go see a picture of my family on this page and get them to go surf there. It's very easy to get people to go surf to anywhere you want them to surf. But if there's a cross-site request forgery vulnerability inside of this application they're on, by that customer service agent visiting the wrong page while they're logged into this application inside of the same browser, an attacker can actually launch an attack back at that application if there's a cross-site request forgery vulnerability there. Okay. So it's something that we are concerned about. Network communications. When we're doing testing on network communications, two main subtasks that we look at are doing the RF packet analysis, looking at the RF signaling, as well as looking at the network protocols themselves. RF packet analysis we don't do a lot of, because RF packets, we should assume that RF packets, that there's no security there. All security should be up at the network protocol layer. Some of the vendors that we work with will say, well, we have security in the form of frequency hopping for our RF spectrum. Okay, frequency hopping is not a security feature. It doesn't do anything other than breaks up the communications across a couple different frequencies I have to attract. One of the most complex frequency hopping patterns that's commonly available that's being used commercially is actually Bluetooth. It's one of the most complex with its frequency hopping. And Bluetooth has been shown with Bluetooth that we can successfully capture all of the traffic inside of Bluetooth and reverse engineer the frequency hopping pattern being used. So it's not a security mechanism. So generally, I don't usually recommend electric utilities spend time performing RF analysis. If they want to, great. If this is something that a vendor would want to perform, excellent. However, we always want to look at the protocols and try to do an analysis of the protocols. When we're doing this, it's very straightforward. Generally, when we're just talking about the protocol analysis on the right-hand side, one of the biggest things that we're looking for, if we're working with proprietary protocols that we can't reverse engineer, Wireshark doesn't have a dissector, we don't have enough time in the engagements to write a dissector or reverse engineer the protocol, what we want to at least do is do a cryptographic analysis of the communications to see if it's encrypted, and if it is encrypted, see how well it's encrypted. Okay, so this is a histogram analysis that we perform. This is a tool that basically will go through and collect out just the payloads of each one of the network packets that we have. So it cuts off all the headers and looks at just the payloads and does an entropy analysis across it to see how random the data is. If we have perfect encryption, you want to see something that looks like on the top. Okay, this is something where all the different hex values inside of the payload are evenly distributed. Okay, if you look at the bottom, this is something that still has been encrypted. This is something that has been encrypted not as well, though. Okay, we're seeing that some of the character sets are being used much more frequently than the other ones. If you ever see something that's not encrypted at all, then quite often you'll see a spike right in the middle of where a lot of characters are being used, and very few characters being used at the beginning and very few characters being used at the end. The reason why is quite often we have ASCII being used for a lot of the unencrypted protocols, and so you'll see a spike right in the hexadecimal range where ASCII is being represented. Okay, another thing that we'll usually test for is if we'll try to identify what types of cipher modes are being used. Almost all of the embedded field devices that you look at are going to be touting that they're using AES encryption and that it's military grade. Well, unfortunately, use of that one single algorithm isn't enough to evaluate its security. We really need to look a little bit deeper and actually look at what cipher modes are being used inside of AES. For instance, one of the cipher modes, CTR, which we will occasionally come across, is very, very insecure, because if you have just one single combination of a packet that's been encrypted and a packet that's been unencrypted, okay, if you have that one single pair, you can actually unencrypt anything inside of the stream you have, as long as you have a continuous connection of streams using very, very basic simple math. Something you could script very easily in whatever scripting language you want. So this gives an example of how this is being done with a very, very simple Python program. We don't show you the Python code, but we show you we do show you the Python code right there. Just a very, very simple algorithm.
Justin?
Yes?
Which tool is used for cryptographic analysis?
With the cryptographic analysis, there are several different tools that are out there. The one that I usually prefer to use, if you go over to a good friend of mine, Joshua Wright, his website is Bullhack for Sushi. If you just go through and do a search for cryptographic analysis or histogram, it will point to one of his tools that he has written. It's a Perl-based tool that you can use to feed it a PCAP file, and it will strip out all the headers and just use the payloads themselves. So that's something that's not commonly available. I'm working on a new distribution, a penetration testing distribution, very similar to Backtrack. One that's specifically for energy sector, though, with the energy sector tools. This is something I'm hoping to launch next month. So keep your eyes open for that. I'm hoping to launch that at Black Hat next month. Okay, then for the embedded tasks. The embedded tasks are probably the more interesting area that most of you probably haven't worked with a lot yet. Okay, with the embedded systems there, primarily we're going to be looking at different components, electronic components in the systems themselves. These are going to be trying to get information that's stored, or data at rest, on the EEPROM, the flash, the RAM memory, and the microprocessor storage. Okay, we're also going to look at data passing across the electronic buses between the different chips on the boards. So with that, we're going to capture that information and try to extract out anything that's interesting to me, something an attacker could use. And then we also want to look at any of the input ports. On the smart meters themselves, there's a little optical port. On some of the PLCs and the IEDs that are being used inside of the SCADA realm, there's quite often a serial interface on them that you can actually connect to for an administrative port. So we want to look at those as well. So when we do penetration testing, we break those into several different subtasks where we look at the components, we look at the field interfaces, anything that's on there, and then optionally, if there's enough time, which usually it's not something most people want to spend money on because it's rather time intensive, we can also do the firmware binary analysis and do reverse engineering of the firmware images themselves, looking for flaws and vulnerabilities. Okay, so this is a breakdown, a little bit more in detail of each one of these major phases. So you can see over here, I'm going to go in a little bit more detail of some of these electronic component analysis. When we're working on these, the very first step we need to do is we need to disassemble the meter itself so we can gain access to the boards. Then we want to analyze the circuits to try to understand what the circuit's doing and analyze what are the different components being used. Okay, this quite often is going to entail getting out what's it called? Not a microscope, a magnifying glass. Get a magnifying glass out and try to identify the actual chips, the part numbers on each of the boards. Once you have the part numbers, then you're going to want to go to the next step, which is the data sheet analysis. Identify all the data sheets, collect the data sheets, look for issues or vulnerabilities or ways you can attack each one of these chips based on the components that we actually see and the functionality we see inside of the data sheets themselves. Once we know how to interface with each one of these components and what their functionalities are, then you want to connect to any of the components that store data. You want to connect directly to them to see if you can dump any of the data at rest off of them. Okay? Then you want to try to look at all the buses between these components and try to capture data while these devices are in normal operations. Try to capture information off those. In the smart meters, that means that you have to hook up your bus snooping components to sniff the data, and then you have to power the device on so you can capture the boot process to see if the firmware image is being passed anywhere on the bus, and then catch the initialization for the network traffic to see if any keys are being passed on the network traffic themselves. And of course, this is something you always have to be very careful with, because when you're working with smart meters, power is usually in the United States either 110 or 220, and probably pretty much 220 here for the most part. And so if you're touching the wrong thing at the wrong time, you will feel it very acutely. In fact, a very funny story, I mentioned Josh Wright, a good friend of mine. One time Josh Wright and myself were testing the meter, and when we do the test, usually the chips that we're working on are surface mount chips that are very, very small pins. And instead of using traditional electronic leads, we actually use syringes, the ones that give you the shots in the arm, medical syringes. So we'll use these so we can actually get the smaller pins. It's a lot easier to do it. And one time he got hit with the 220 volts, and he jumped, dropped the syringe, and it landed in his shoe, right next to his toe. It didn't hit his toe, but it was sitting there sort of wobbling in his shoe. So, yes, so lots of fun with doing our embedded testing. Once we have this data, either from the bus or from the data at rest, we want to start analyzing it. We'll do a strings analysis to try to identify if there's anything commonly there. We'll do an entropy analysis to see if we can identify encrypted data inside of there. Then we can also do a systematic key search to try to identify anything that might be a password. Just in the interest of time, let me go a little faster here. This is interfacing with the chip itself once we've taken it apart and connected to each of one of the wires. We don't generally solder wires to each of the components. This is something that we are doing with extended testing. So it's something that we went ahead and soldered the wires to it. Most of the time we use little clips, little micro clips to clip to each one of the pins. So it's temporary, we can remove that very quickly. Okay, and then we also will lift up some of the pins sometimes. Occasionally, there's going to be a pin or a chip that's speaking on the bus or controlling the bus, and we need to get rid of it. Usually we can go ahead and just reset that chip itself by pulling its reset pin high or low. Sometimes we have to remove the pin and lift one of the pins. Okay, this is an example of dumping data at rest. So once I've connected to an EEPROM device, this shows at the very bottom it dumping the data back out of the EEPROM device. Okay, and this is bus snooping. So this is once I actually have my communications. This is, you can see the syringes that we use here inside this diagram. When you get the actual presentations, you'll be able to see the syringes better. But we usually will sniff data between two different points with a grounding that you can't sleep to be able to capture any of the data that's coming off of these devices. Once we have this data, we're going to want to go through and try to identify any of the cryptographic keys or any of the firmware that we actually have inside of this device. So this is we're going to use several different methods to do this. Here is one example of doing a systematic key search. So this will actually go through and try every single possible combination of bytes as a possible password if you have, or I should say cryptographic key, if you actually have some type of encrypted element you're trying to decrypt. This usually requires custom tools for everything that you're doing. I'll show you in just a minute, I'll show you with Zigbee how we actually do this with Zigbee with a RAM dump from a chip. We can actually find the Zigbee key by searching through the RAM dump. Okay, then we also want to do an entropy analysis. Here we actually do very similar to what we do with the network, but we're doing it with data that we're pulling off of some of these chips. You can see that one little teeny spike right in the very middle. This is the asymmetrical key that's actually stored inside of this firmware that we dumped off of one of the boards. Okay, the reason why is asymmetrical keys are randomly generated. Okay, and so if you ever do an entropy analysis test and you see something very small that's 64 bits to 128 bits, sometimes a little more, of high entropy elements, and it's the only thing there, it's most likely the asymmetrical key that you just found. Okay, now, here's the contact information. Before I finish up, let me go ahead and take a couple of questions. Let me go ahead and show you very quickly a demo of just a couple of these tools. So if I look right here, I have two different files here that I have captured. So one is the memdump.bin file. This is a binary file we've actually captured from a ROM inside a RAM component inside of a chip themselves. Specifically, this is an Ember chip. It had a vulnerability that allowed us to get in and access all the content inside of RAM that was actually up and running. So we actually have contents of RAM now from one of the embedded devices. Okay, using this memory dump, we have a special tool that's going to go through and try to identify the key. But when I have the memory dump, the very first thing that I do is I'll usually go through and just look at a hex dump, try to identify anything that's there. Okay, so this is just nothing similar here if you're looking at binary files. I will just very quickly go through and look at the data that I have. We're working with embedded devices, so it's usually fairly easy just to look through it. It's not like trying to pull RAM off of a server that's monstrous. Okay, that's actually the whole dump right there. Okay, so I'll look at that, see if there's anything there. We'll usually go through and do a streams analysis. Okay, just pull out all the streams that we have, the ASCII streams, and you can do this for Unicode, ASCII, whatever streams that's used. I'll usually look at a couple different ones. This is just the default string search. So I just want to look for anything that looked like it might be a password. Quite often we'll actually find when we look at the embedded components that if they're using a symmetric password that's user chosen, we'll usually very easily identify it because it's usually related to something with the company or the product or the vendor. And so that's something you can always try once you find it inside of the strings analysis. If you don't see anything inside of the strings analysis and looking just at the raw dump itself, then another thing we want to do is we want to go through and if we have a tool or write a tool, to try to do that systematic search through the memory to try to use everything as a possible key to decrypt something or to verify a signature or something. So in this case, this is a Zigbee capture. So I can see in my 802.15.4 encrypted sample, this is a packet capture of a Zigbee interface or Zigbee traffic that is encrypted. Of this same exact system we dump the memory off of. So what I'm going to do is I have a specialized tool here called ZD Goodfind. This was also written by Joshua Wright in partnership with Travis Goodspeed. That will systematically go through that RAM dump trying to decrypt this packet. So I'll go ahead and run this tool. You can see that it very quickly goes through 6,264 guesses, trying every single possible combination to decrypt that Zigbee packet. And it successfully found that it decrypted that Zigbee packet and tells you exactly what the key is right there. Okay, so this is a technique that they use you may, if you ever go back and research how they initially broke the encryption in Blu-ray devices and HD DVD systems, this is the same thing that they did by capturing RAM of a running DVD player inside of a Windows machine, systematically trying every single possibility until it extracted out the key. This same exact thing works anywhere. Okay, so if you're ever trying to find cryptographic keys out of a bulk data set, write something that will try every single possible combination inside of the algorithm to see if you can actually get something to decrypt the traffic. Okay, we had a question right there.
So you showed the entropy dump, right? The entropy of the dumped ROM, and you showed the spike, right? So what was the x-axis representing there? So it has
they were hexadecimal characters.
The x-axis.
I believe the x-axis was hexadecimal characters. No, that one wasn't hexadecimal characters.
Number of samples it takes.
Pardon?
I think the number of samples you are taking, 1,000, 2,000 samples.
No, this one, actually, no, maybe that's what it was. I think that was actually hexadecimal characters, and this is the number. That's what it was. It was actually looking at the hexadecimal, rating the hexadecimal characters on the y-axis. On the x-axis was the actual offset, the hex offset.
Now, when you have a AES algorithm, you have different blocks. So you capture 2,000 blocks, 4,000 blocks of that. So do the entropy analysis.
I can understand entropy analysis, but I was trying to understand what the x-axis represents.
Yes, yes, that was the number of elements that we are doing, and in this case, they were actually hexadecimal elements.
I have a question.
Yes.
See, in case of this smart grid, NIST is coming out with the requirement document. Does they have come out with any control-specific matrix where you can find out these are the some of the interfaces the vulnerability exists, and I have these the controls I can apply, and then I can take care of this.
Yeah, and you're specifically asking about the NIST interagency report,
Yes.
7628?
Yes.
With that one, that's more of a guidance, and that's not going to be a requirement document ever. That's something, it's not written. I was one of the primary authors. In fact, if you ever look at that 7628, I led the security architecture team in the creation of a portion of that document, and almost all the diagrams were actually created by myself and my team. So with that document, it's not meant to be a requirements document, it's simply made to be a guidance document. So I hope that there's never any requirements come back out of it. But one thing the Department of Energy is doing, they're currently right now working on a guidance document to performing risk assessments and the measurement of metrics inside of the risk assessments. So this is something that's currently going on right now, and the Department of Energy expects to have it deliverable out, I believe, in 3 months.
Yeah, because if you do the pen test in case of smart grid, your parameters will be different, like voltage, current. It may not be the same when you do for like your servers. Your parameters will be different in the
Right.
So you need a different kind of risk analysis, and you can find out the.
No, that is exactly correct. One thing that I've been trying to stress to all the policymakers back in the U.S. is penetration testing is critical. We need to do penetration testing to find these vulnerabilities, because penetration testing turns everything on its head and looks at it in a reverse engineer's perspective from a ground-up methodology. But penetration testing cannot be used as an accurate metric between multiple different organizations or between testing groups for the same organization, same system. It's simply something that the nature of penetration testing can't be measured in a metrics and comparison type system. So my recommendation for penetration testing for policymakers is that when they create regulation for critical infrastructure, that they simply make the requirement that a penetration test must be performed by a competent entity. And simply just make it as a checkbox that it must be performed, possibly specify on an annual basis, but not to try to leverage any of the metrics that come back out of it, because the metrics simply aren't usable in that method. It's not perfect. It's not something that will guarantee that people will go through and do a real penetration test and really look for the vulnerabilities, but it will actually at least get them looking in the right direction. Any other questions?
Is there a different way of protocol analysis for Modbus and other protocols?
I'm sorry, is there a protocol analysis method for Modbus?
Yeah, Modbus.
Yes, if you have Wireshark actually has dissectors in it for Modbus and DNP3, which are going to be the two most common SCADA protocols you have. Wireshark, for those that are looking at SCADA systems, one of the newer protocols, I should say a suite or family of protocols you'll come across, is IBC 61850.
Would that also include RP570?
Huh?
Would that also include RP570?
IBC 570?
RP570 standard for protocol for SCADA systems?
I'm missing IP 570?
RP.
Oh, RP 570. No, RP 570 is, I believe, is a different protocol. I don't think it's part of the IBC suite.
But that would be included in the SCADA analysis?
Yes, it would be one of the protocols that could be used. However, I don't know. I don't believe Wireshark has dissectors for it. It may or may not. You'd have to look. But that's one thing that we always do more people on. If you get in this field and you find protocols that Wireshark doesn't support, please write dissectors and share them out with the world. We are about this close to getting the most common protocol for smart meters, which is C1221. There's a dissector that's available for it. We haven't gotten it added to the main trunk for Wireshark. However, you can actually find it on Wireshark's page. It has been submitted, and it's actually been written by one of the security leads for one of the major smart grid vendors. So it's a very, very good dissector. So that's something else that's out there.